Welcome back, dear participants of the Photonics Days, and a very warm welcome now to all our audiences who are together with us here via the YouTube stream in order to see the Nobel Talks, the next highlight of this day. We are very pleased to welcome here Nobel Prize winner Professor Reinhard Genzel to give his Nobel talk. Unfortunately, he cannot be here with us in person, but he will join in a moment via live stream. Before we come to Professor Genzel, I'd like to welcome here in the studio with me Professor Andreas Tünnermann, Director of the Fraunhofer Institute of Applied Optics and Precision Engineering here in Jena, and also Professor Peter Zipfel, Chairman of Beutenberg Campus, who will in a moment introduce the Nobel Talks. As a remark, we are all here sticking to the 3G rules, meaning we are all vaccinated or tested on a regular basis. I would like to start with you, Professor Tünnermann, with some question. How about you introduce Professor Genzel to the audience, please?
Oh, it's a great pleasure to do this, of course. Thank you. Well, Reinhard Genzel is one of the directors of the Max Planck Institute for Extraterrestrial Physics in Garching. He is a professor at the University of California, Berkeley, and he's professor at the Ludwig Maximilian University in Munich. He's a scientific member of the Max Planck Society and a member of the National Academy of Science in the United States. His research interests include astrophysics of nucleus, galactic nucleus, star formation, kinematics, and cosmic evolution of galaxies, massive black holes, and he's experimentally working in infrared, submillimeter, and millimeter astronomy. Reinhard Genzel has received numerous honors and awards, including the Shaw Prize or the Crawford Prize in Astronomy, and in 2020, he received the Nobel Prize in Physics jointly with Andrea Ghez for the discovery of a supermassive compact object at the center of our galaxy.
Thank you very much. Could you also specify the point of contact between Professor Genzel's research and that of the Institute here?
Well, we have several contacts to our colleagues in astronomy. Our main research activities here at the Fraunhofer Institute include the development of optical instruments to be used for mapping of stars, for example. And a very prominent example of an instrument we have developed is the Gaia instrument. It's a satellite-based system which allowed, in fact, for the mapping of billions of stars in our galaxy.
Thank you very much, Professor Tünnermann. I'd like now to hand over to Professor Peter Zipfel, and so that you can introduce Professor Genzel. Thank you.
Thank you very much. And ladies and gentlemen, it's a great pleasure for me to present this Nobel lecture as chairman of the Beutenberg campus. And the Beutenberg campus in Jena coordinates the activities of 9 research institutes and 1 center for applied work that are all located here in the center of the campus, and they form together a network of excellence. The campus combines life sciences, physics, and optics. And to give a highlight and in this way understanding on the activities in the field, the Nobel lectures, Nobel Gespräche was initiated. And the idea is that well-known, respected scientists and particularly Nobel laureates present their work to the public and show what the activities are performed at this place and institute. And for many years now, this important lecture series to the public is also supported by the Karl Zeiss Stiftung. And I'm very happy that the CEO of the Karl Zeiss Stiftung, of the foundation, Dr. Streiter, is joining us today. And I want to thank him and also the foundation for the continuous and generous support. Please allow me a very short personal view. I work here at the Leibniz Institute for Natural Product Research and Infection Biology, and our work focuses on host microbe interaction on a very tiny microscopic level. And based on this, I'm always impressed by the other dimension, by larger areas, and this is the field that Professor Genzel is working on. So he works on large objects, and the sum of one he's dealing is 4 millionths the mass of the sun, and so this is just the other side of the spectrum in this way that we see. And with this, I'm very interested to learn more about this other dimensions and also on the 40 years of journey to this topic and area. And with this, I say hello and welcome to Garching, to Professor Genzel, and the stage is now yours, and we are eager for your pleasant presentation.
Okay, Dr. Tinnemann, it's a great pleasure for me to be here and talk to you. Indeed, I would say what you probably will see in my talk is that whilst the subject of our studies are indeed quite far removed, the way we do the studies, our experimental techniques, are very close to what you do in your daily lives. We use lasers, optomechanics, very, very sensitive detectors, and so forth. And I'll try to explain that to you in my talk. Now, the title of the talk I've given you is A 40-Year Journey. You will see why that is. What we've done in 40 years in several steps is to come ever closer to the center of our Milky Way in order to test the hypothesis, and I will describe where that comes from, that there might be in the center of our galaxy, in fact, every galaxy, a massive concentration in form of a massive black hole. Now, of course, this kind of work we do with big telescopes, optical telescopes, but in this particular case, as you will see, we cannot use optical wavelength. We have to go to somewhat redder wavelengths, infrared wavelength, in order to then look into the center of the Milky Way. And much of the work I'll describe to you has been carried out with the telescopes of the European Southern Observatory in Chile, the very large telescope, and I'll explain that to you. Now, of course, this kind of research, as you will see, takes some time. Technical innovation is very, very important. And so let's go on to this 40-year journey, and I'll tell you why we are so keen to understand whether there is a black hole. Now, you may recall that about 100 years ago, in fact, it's 105 years ago, Albert Einstein introduced in Berlin his new theory of gravitation, where he embedded what he had learned in the theory of special relativity about the world coming close to the fastest speed we have in our universe, which is the speed of light, and the world of Newton, which is dominating the interaction between celestial bodies. And so he, in his theory, as you may know, used a mathematical formulation of gravity, which explains the gravitational interaction between objects as a warping, as a curvature of space and time, in which then other objects and also light have to follow the path of least distance. So this theory is a fairly complicated mathematical body, and it took quite a while to find solutions in special cases, and then also understand the consequences. 1 year after the publication of the theory, the general theory, Karl Schwarzschild, up on the right there, found a solution for a spherically symmetric mass distribution. And to his surprise, to everyone's surprise, one finds in there a characteristic radius of an object, for any mass, which is called the event horizon. And that basically expresses the fact that light itself also sees gravitation. So that if the gravity in the surface of an object is large enough because the combination of mass and size is compact enough and massive enough that light cannot escape, well, then you have no more communication from the inside to the outside. So that's what we would nowadays call a black hole. A very weird construct at the time. How could that be? Such objects obviously had not been seen. Now, it took another 50 years to really formulate the theory also for other parameters, and we now know that these black holes actually are fairly simple objects according to the theory. They have only 3 numbers you can associate with them, and then you know everything about them. Mass is 1. The rotation or the spin of the black hole is another one. And the third, which in astrophysics actually turns out is not important, is electrical charge. So with these two or three numbers, quantum numbers you might say, these objects are fully described, remarkable, even if they are billions of solar masses, as you will see. And then finally, Roger Penrose, who received a Nobel Prize together with me and Andrea Ghez last year, showed that these specific solutions, which Schwarzschild and Kerr had found, actually are generally true, and that actually such objects might exist. But then it took quite a while in the mid-60s until the first candidate objects for such black holes were found. Very bright X-ray emitting binary stars were the first ones, which we now know to be stellar black holes. The second one were objects which the radio astronomers, then mapping out the sky at radio wavelengths for the first time, found, and these are the so-called quasars. When you look at such a radio quasar in optical light, then you see a faint star-like object on the sky, not very impressive at all. But then when you look at the wavelength of spectral lines in the optical, which Martin Schmidt did with the big 5-meter Palomar telescope in 1963, then you find that the spectral lines of hydrogen, helium, and so forth are all redshifted by about 16% in the first object which they had found. 16% could probably, and that was known at the time, be a consequence of distance, because the universe is expanding, and the further away an object is, the more redshifted its emission arrives at Earth. So 16% redshift then transforms into a distance of about 2.4 billion light years, which at the time was unheard of. Nowadays, we know objects which are still further away and only, relatively close to the Big Bang. So these quasars are spectacular objects. And if you then convert the amount of radiation we see into the actual amount of energy radiated, given this large distance, you end up concluding that these objects must have masses of millions or billions of solar masses and luminosities which are 1,000 to 100,000 times the mass of the entire Milky Way with its 100 billion stars. Remarkable. But now, of course, the question is, how could you generate that much radiation? And so a number of theorists thought about this in the 1960s and early 1970s. Amongst those, the famous British astrophysicists Donald Lynden-Bell and Martin Rees, Rashid Sonyaev in Russia, and Roger Blandford, then in Cambridge and later in the US. And they basically came up with an almost absurd conclusion, namely that these objects which we are looking at are black holes. Well, how does that work together with the fact that I told you before that black holes are objects from which light cannot escape? Well, very simply, if material falls into black holes, forms often, we think, a so-called accretion disk, because angular momentum has to be removed slowly through friction processes, and falls in, then before the material disappears behind the event horizon, it can release up to 40% of the rest mass energy of any particle. 40% of mc squared. That's 100 times more energy per mass than you release in fusion. And so that's a plausible theoretical hypothesis for the explanation of these quasars. So how could we prove this? Now, astronomers found spectacular high-energy phenomena associated with the quasars, like X-ray radiation, gamma-ray radiation, or streams of relativistic plasma radiating in the optical to radio, which we call jets. So that likely shows that this is a very energetic, compact object with strong gravity, but must it be a black hole? Could it not be something else? And that's really the question which the observers and experimentalists were faced with in the early 1970s. And how would you test that? Well, by looking at the effect of the gravity of a black hole onto the environment. So if you think of the solar system, then of course we know Kepler's laws hold. The sun is the most massive object in the solar system, and the planets are on bound orbits, ellipses or circular orbits. And Kepler's laws tell you that because the sun is dominating, the most distant planets move slower on their orbits than the innermost planets. So turn that around in your mind, switch off the light of the sun, and Tycho Brahe would have made the same measurements of this kind of a solar system. Kepler's laws still hold. You would find that the planets which are further away move closer, slower than the ones close to the sun. So that's the kind of technique which we are using in astronomy nowadays to check out this hypothesis. Now, obviously, quasars are very far away, and so the question is, how do you make such an experiment? Well, Linden, Bell, and Rees proposed that perhaps not only these distant quasars, but other galaxies, including our own, might have such massive black holes. Now, let's go on a trip and fly from the Earth, which is at 27,000 light years away, into the center of the Milky Way. We see all these stars of the Milky Way, but we also see that our optical eyes, so to speak, are dim, see ever dimmer radiation from the center through interstellar dust particles, which dim the light by a large factor. And so that's why we have to go to longer wavelengths to make measurements. And then finally, look into the very center of our Milky Way. With techniques which I tell you a little more about later, we can make pictures like this of the central few light years in the infrared of our Milky Way. And what we find is a tremendously dense and massive concentration of stars and also gas. So that's, in fact, if you like, our test particles, our particles which we use to look for a central mass in this region. Now, the radio astronomy community also looked at the galactic center at that time and found a very compact radio source, which we call Sagittarius A star. With modern techniques of interferometry, we can now show that this radio source has a very, very, very small size, only 40 micro arc second. That's about 20 centimeters at the distance of the moon. So it's a very compact source. In fact, that is a little bigger than the event horizon size of what you might expect a black hole to be of a few million solar masses. So these observations in the 1970s, so began to show that maybe this is a wonderful laboratory to check out the hypothesis of these massive black holes. But you must have equipment, technology in the infrared. Now in Berkeley, the Nobel laureate Charles Townes at that time had changed his field. He got his Nobel Prize in 1964 for the invention of the laser and the maser, but then developed an interest in astronomy and then moved to California to form a group of experimental infrared astronomy. And they had the first spectrometers which could look through this dust and look at the center near Sagittarius star at gas clouds, ionized gas clouds, which you see here in pink, and neutral gas clouds, which you see there in green. I then joined this group in the early 1980s, and within a few years, we used the spectroscopy evidence to measure the Doppler shifts of the spectral lines coming from this gas streamers, and could show that this indicated indeed a concentrated mass. Just looking at the velocities of the gas clouds as a function of distance from the center. And on the left side, you see what we found. As you go far out, many light years or hundreds of light years from the galactic center, then the mass changes with distance and gets ever smaller as you go inward. That's a sign of an extended mass configuration, and is made up essentially by all the stars in the nucleus of our Milky Way. But then inside of about a few light years, the mass doesn't change anymore. Stays more or less constant at a few million solar masses. So in 1985, we in fact published a fairly confident Nature article saying there is a massive black hole of a few million solar masses in the galactic center. But of course, science works only if people actually can confirm and are convinced by your arguments. And many people were skeptical that the gas technique was really convincing, because gas can also be pushed around by magnetic fields or stellar winds, which we know are very strong in this region. So maybe we have to be a little careful. Also, the mass, which I showed you, of a few million solar masses, is on a scale of about 1 million times the event horizon of a million solar mass black hole. So many people felt, well, okay, why does it have to be a black hole? Could it not be, say, a cluster of stars, faint stars, neutron stars, or something like this? So by the mid-80s, we had the first evidence, but we knew we had a lot of work to do. We had to go to a new tracer, stars instead of gas, which are more reliable for measuring gravity, and we had to go further in. So that requires technology. And so the technology we had to invent are detectors in the infrared, which could do imaging. And very importantly, we have to correct for the refraction and winds in the atmosphere, which bend and destroy sharp images. Of course, you can go up in space, but the technique which we have developed over the years is called adaptive optics. You basically have sensors in your system to measure how the wave fronts are bent, and then you have a deformable mirror in the path of your instrument, which then can correct that, and then you can then sharpen the images. This kind of technique started to get possible with modern detectors and optomechanical structures and of course fast computers in the 1990s. Nowadays, all the big telescopes are equipped with adaptive optics and can produce diffraction-limited images. Even the biggest telescopes. Now, to do adaptive optics, you need to have a star or a point mass, point light source near the objects which you want to look at, and not always do you have that. If you do, well, then you can get, as I said, diffraction-limited images. But sometimes you don't. And in that case, we bring our own star with modern photonic instrumentation. We shoot a laser tuned to the sodium D line into the upper atmosphere, and in the upper atmosphere at about 90 kilometers altitude, we have a thin rain of sodium atoms coming from outer space where meteorites fall into the Earth from time to time, and that gets, vaporized, and then we use backscattering, resonant backscattering, by these sodium atoms in the upper atmosphere to generate an artificial star, a laser star, which then penetrates through the atmosphere and which we can use to do adaptive optics with. So this kind of technology and much more, which I don't have time to explain to you right now, really was necessary to go the next step and look for the motions of stars on very small scales. So in the 1990s then, this technology indeed became possible. And after a few years, our group, working with the telescopes of the European Southern Observatory in Chile, and then the second group, Andrea Guess and her colleagues at the University of California, Los Angeles, using the new Keck telescope on Mauna Kea, were able to look for the changes of position of stars with time. And I show you here in this picture 3 different images in 3 different colors, red, green, and blue, which are 3 different years. And you can immediately see that near the little cross, which is the position of Sagittarius A star, on a scale of only a few light weeks, the circle is a light month, you can see that there are stars which clearly change position in a matter of a year or two. And if you look at the arrows, then the velocities which you derive here are thousands of kilometers per second. That had never been seen before, immediately shows you there must be a very large mass. In fact, you can calculate with Newton very simply that given the size of a few light weeks and then the velocities of at 2,000 kilometers per second, there must be a few million solar mass concentration. Must it be a compact mass? Yes, because if you look at the images, then the outer stars don't show much of a prism effect while the inner ones do. And that's the Kepler's laws at work again. That shows you that the mass really must be concentrated on or very near the radio source Sagittarius star. So by the mid-90s, both groups had found the same thing. Many people were convinced, yes, the galactic center is an excellent case for such a massive black hole, and all the measurements are consistent with it. Theoretical work showed that other configurations, like for instance, as I said, faint stars and so forth, were hard to concentrate in a volume this small. But must it be a black hole? Well, when analyzing the situation, of course, we apply general relativity. And are we sure that general relativity, which is so well tested in the laboratory or in the solar system, also applies to such an incredibly relativistic object as a black hole? And that we didn't know. What would we need to test it? Well, we would need to come still closer, and we should do more than just look at 2-dimensional motions on the sky. We want to have the full 3-dimensional information of an orbit. And for that, we only can hope that nature gives us such objects, stars which move into the central region. And indeed, in the galactic center, this was possible, and a star came in 2002 and turned around the loop, so to speak, at a distance of only 17 light hours from the black hole. The whole orbit takes 16 years, and in 2002, the star was a mere 17 light hours away from Sagittarius star. 17 light hours, that's solar system scales. That's about 3 to 4 times the orbital radius of Neptune. And again, if you measure the velocity there, the orbital velocity at that point is about 7,500 kilometers per second, 2.5% the speed of light, and then use the distance, well, then you can get a mass, and that turns out to be 4 million solar masses. So the same mass which we had known before from the gas measurements and then from the statistical measurements, but now on much smaller scales of about 1,000 light years. So by 2002, we were well on our way to convincing many, many people. In the next years, we actually were able to not only show these motions for one star, but a whole set of stars, which actually is a paradox, because these stars, when you look at them, are stars which are fairly young. And if you take a star and place it at a few light years away from the black hole, it takes several billion years for the star to sink into the center. These stars, however, are much younger. So it's actually a puzzle how this is possible. And we understand it now, we think, by the fact that even in the vicinity of such a tremendous monster of a mass, star formation can occur under certain circumstances. And sometimes stars are coming in as binaries, and one of the binary partners gets stuck. And so that's the star cluster dancing around our own galactic center. So this is a fairly convincing picture we have, but it's still not sufficient to be very sure that this must be a black hole, because we assume general relativity. Now, because of the 16 years, we knew that the star would come back for its next Perry approach in 2018. So what could we do in the remaining 10, 11 years to still get better? Well, on the site of the European Southern Observatory's very large telescope, Paranal, in southern Chile, you see there are 4 8-meter telescopes. One of them we use so far for our measurements, but what about the others? Can we not combine them as an interferometer like radio astronomers do, and thereby then generate an effective telescope of about 130 to 200 meter diameter and get that resolution? So that was our idea, and extremely difficult to build such an instrument. And we made a movie which shows you what we all had to do to get this thing to work. It was led by Frank Eisenhower in my group in a consortium of European institutes and ESO over the period 2005 to 2015, and the instrument is called Gravity. And so the movie, which you now will see, we have called The Last Millisecond of the Tortured Photon, and you will see why we say so. So this basically shows you what we do to combine the light of the telescope. So here's your light beam coming in, hitting one of the telescopes, primary, secondary, and tertiary mirrors. And now the light has to be brought downwards in order to be able to combine them. And so it takes quite a number of mirrors in the telescope structure to do so. The next thing is we have to use adaptive optics again for every one of the 4 telescopes. So here we have a bench where we analyze the light and are able to correct the wavefronts and straighten them. And then the 4 light beams from the 4 telescopes have to be aligned in this tunnel and then finally brought together in our instrument. This is a cryogenic instrument in order to minimize thermal noise, and also vibrations. So here's one of the beams from one of the telescopes, and we need to now do some more alignments and basically checks before we then can actually attempt to combine the light. Now, a great trick here in our instrument is that we actually split the light in the focal plane from two different locations. One where there is a bright star in the sky, which we can use for tracking the fringes in the interferometer, and the other one where we want to look for the moving star. So we have to do this for all the four telescopes, and we have to also correct the path lengths, which merely have to be accurate to a few nanometers. And we do this in monomode fibers. So the light is now going through monomode fibers. In these bundles, we can stretch the path lengths by a few micrometers. We can also manipulate the polarization of the light in these bundles here. And then finally, we use telecommunication technology to combine the light in a chip of only about a centimeter in size, where we can now take the four beams and make all the combinations of the different telescopes. So four beams make 6 independent combinations of light, and this is done in this little chip which you see on fused silica. And then we sample the fringes at 4 different phases and finally disperse the light so we can get spectra. So this is a very complicated instrument, and the detector which you see here was a detector developed such that it doesn't have any noise anymore, even at a readout rate of about 1 kilohertz. That's really tremendous achievement, and allows us to make very sensitive measurements, now with a resolution which is another factor of 20 better than a single 8-meter telescope can give you. So let me show you what we found. Gravity, this instrument, has very sharp eyes. We can resolve with it a Eurocent coin on the moon. And a Eurocent coin on the moon is about 10 microarcseconds, which indeed is the event horizon size of a 4 million solar mass black hole. To show you and demonstrate you the progress over the years, let's start with when we started with the first detectors back in the 90s without adaptive optics. Then we could see the first individual stars. I told you that the radio astronomers then found a radio source in the vicinity. Then I mentioned to you adaptive optics, which now can basically sharpen the wavefronts and get to higher resolution. And with an 8-meter class telescope, we can again improve the resolution by about a factor of 20 compared to what you can get with a normal telescope. Now with gravity, we can look at the region right next to the radio source, Sagittarius star, in the very center, and resolve a region of a mere 100 milliarcsecond in size. So what we see, this is an image from earlier this year in May, is the radio source, the star, plus 4 other stars, a busy region, and all these stars move. And with the interferometer, we can see this motion from day to day and from week to week. And within one half year, we can basically see these 4 stars moving around the galactic center. This star S29 is our new world record holder, if you like, and comes very close to the center and moves with 8,500 kilometers per second. That's terrific. That's incredible. These are our, so to speak, microscopic tools to test gravity. So what can we find with such detailed information? Well, we can actually map out the motions of these stars on scales of, as I said, of the solar system with incredible precision, and thereby then infer from that the orbits of the stars in 3 dimensions, as well as the mass of the center, the mass distribution, whether it's extended or not, and also the distance of the galactic center. We can now actually measure the mass to about 0.2%, and the distance to the galactic center to about 0.3, 0.4%. So that's incredible detail for astronomical measurements. And so these motions from night to night we can determine and therefore get high precision. And that gives us now the opportunity to see the effects of general relativity in this unusual region. The first effect is the effect of gravity onto the photons themselves. So if you have a star which is moving into the central region near this big mass, well, then the photons from the star have to climb out of the potential well, and before they reach us, they are redshifted by a certain amount. Now that we can see in the experiment by subtracting the Newton orbital motion, such that the Newton orbit is just this horizontal gray line, whilst relativity would predict the red line, which is this red shift near Perry. And you see that the data perfectly agree with that. So that's a very significant detection of this red shift. The next effect of general relativity is the fact that in Newton's theory, a planet moving around the sun, if it's only one planet, would stay in orbit which is constant in space. Not so in general relativity. In general relativity, the orbit of a star around a black hole, for instance, precesses. Precesses in the orbit, that's called a Schwarzschild precession. Now, because the orbit of the star is so elliptical, most of the precession actually happens near the Perry approach. Little happens at Apo, at the distance. So if you plot the residuals after subtracting the Newtonian motion, you see that at Apo, these are the red points, nothing much happens. But then when the star comes near Perry and post-Perry, then the deviations are very strong. It's like a kink in the orbit, which is just as expected in general relativity. So that's our second proof that this whole system is indeed following general relativity. But we're still, at this point, quite far away. We can measure very precisely, but we're quite far away from the black hole, about 1,000 times the event horizon size. But we can do better. We can actually look at the black hole itself. The infrared emission from the black hole is highly variable. And sometimes it becomes very bright for a few hours. And that's when we think there are like magnetic thunderstorms in the central region, which we can see and measure then as a function of time, the position of this maximum spot of radiation. As you see in the lower right, what we see is that over a period of tens of minutes, the spot of light moves around the black hole. It's a very difficult measurement by a few tens of microarc seconds, or about 0.3 times the speed of light. So that's clear. Within that region must be the big mass. That's now on a scale of only a few times the size of the event horizon. So over the 40 years, we've come a long way. We started off, as I explained to you, getting the first hints of a massive object 40 years ago, but then followed it inward and saw always the same mass with ever better techniques all the way to near the event horizon size. Of course, we would like to still come further. We also would like to still measure one more property, which we have not, and that's the spin of the black hole. I'll say one more word in my last slide. Now, there seems to be little else but the central massive black hole. It could have been, for instance, that actually it's not a single black hole, but two, a binary, or a black hole surrounded by another black hole, an intermediate mass black hole. That we can all exclude. Also, some theorists have speculated that dark matter might be concentrated near the black hole. That we can also exclude. So it seems to be a rather unique configuration of a single 4 million solar mass black hole, and then a few stars, also some stellar black holes, but nothing very massive surrounding it. So must it be a black hole? Very likely. What's left to do, of course, is to check out some of the most subtle effects of general relativity, which I said already have to do with the fact that there can be a spin. And in the end, of course, to come as close as possible to the event horizon. So the future is bright in this field and has to do, again, with instrumentation in the future. We will improve the sensitivity of the interferometer in the next years by another factor of 100 and hope to then make still better measurements. The radio astronomers are using similar techniques with telescopes spread around the entire globe to look at these black holes and look at the bending of light near the center of such black holes. In a few years, we will go from 8-meter class telescopes to 40-meter class telescopes. Our institute is the principal investigator institute of a large European consortium which builds the first camera for this extremely large telescope of ESOs, which we hope to be ready in about 5 years or so, and will be completely equipped with adaptive optics and laser guide stars and so forth, just like I showed you, and will have still another factor of 6 times higher resolution. And then finally, in 20 years' time or 15 years' time, the European Space Agency hopes to launch into space a configuration of 3 satellites which exchange lasers and thereby measure the space-time variations if a gravitational wave comes by. That's a beautiful way to test general relativity near a massive black hole in some great detail. And so there's a whole host of scientific questions which now are ready to be explored. Inner stars, the spin of the black hole, as I said, the actual tests that mass and spin are sufficient to explain all of the properties of these objects called black holes, gravitational waves. Then, of course, the question how these black holes came about and what their role is in galaxies over cosmic time. We now know that we see such big black holes about 10 billion years ago, a few billion years after the Big Bang. But how far does this go back? When were the first black holes formed and how? What was first? Was it the black holes or was it the galaxies? So there's a lot of theoretical and experimental work to be done, and all of this with techniques which we hope to develop in the next years for ever better measurements. Thank you very much.
Professor Genzel, thank you so much for this amazing talk. I'm quite sure in the audience there are several people who would like to ask you some questions. So we still have, looking at the time, about 10 minutes left. So please go ahead. If you're following this now via the YouTube stream, please just put your question in the chat, in the YouTube chat itself. And if you're following us via the Photonics Days stream, then please use the Q&A window. Just right here to the chat window and to this streaming window which you see. And we also have some people here in the audience, so if some of you has a question, just make a signal to me, stand up, and you have a microphone over there. So while the questions are coming in, we of course before thought about some questions we have, and Professor Genzel, don't be too excited. They're not about your science, they're more general ones, if I may so, but still concern every scientist. We all know scientists are keen to continue doing what they are doing and they're emotional about their work. However, what drives you along all these 40 years of journey? Where did you get all this power to stay on this project?
Well, I mean, of course, I have a, you know, shall we say, a heritage in this, since my father was already a physicist. And in fact, he was an experimental physicist doing infrared work. And so I saw research from my earliest days as a child and got excited about this. Of course, astronomy was not necessarily the only field I would have picked. In fact, I could have equally picked neuroscience. My daughters are doing neuroscience, so that's other fields one is excited about. But once one gets excited about something, then of course it's important to you know, invest yourself, work hard. As I always say in German, von nix kommt nix. You really have to, you know, work very hard. And now I had the pleasure in my younger years to be a track and field athlete. I wanted to go to Olympic Games in Munich. This didn't work out in the end, but it gave me, so to speak, the kick which you need in order to work hard. Now, the other side is luck. I had tremendous mentors. I already mentioned Charles Townes. What a great scientist he was. He passed away 6 years ago at the age of almost 100. And I learned a lot from him. And that's very important, that you have mentors and people who show you where to go, get the sense of where the next steps might be. You have to develop a certain hunting smell, if I want to see this. And also, of course, in experiments, you have to learn what is possible or not. And finally, you have to have people who are willing to walk with you, to go to 8,000 meters with you. And I've always had a wonderful crew of people and an organization, the Max Planck Society, which has allowed us to work 40 years, take high risks, and of course also the resources to do the experiments.
Thank you very much. My father used to say, wer stetes Streben sich bemüht, den werden wir erlösen. It's like the long version of From Nix Kommt Nix. And you already answered another question we had, because we wanted to ask you about your sporty past, and were wondering what you took from your experience as in German it's Speerwerfer, in English it's javelin thrower. And for those people who do not know it in the audience, I quickly would like to introduce that Professor Genzel really was even training for the Olympic Games in 1972 in the team. So well done, another big achievement. We have now questions here from the audience. I would like to forward the first one to you. So someone wants to know, can a person who graduated in the field of measurement, sensors and instruments in general work in the aerospace and astronomy field, and if yes, how?
Of course. I mean, if you look at my own group, the kind of work we're doing requires all kinds of talents. You know, people who really are exquisite experimentalists, like Frank Eisenhower, who led our instrumentation lately. But then you also need people who understand the theoretical side of things. You need people who work with computers, modern analysis tools, et cetera, et cetera. So a team has, you know, a successful team has a whole plethora of capabilities. And I sometimes proudly, and please forgive me, call my team here my Champions League team, because every one of them, female and male, by themselves, top world experts, could be professors anywhere in the world, but have decided to stay over many years because they were excited about the same kind of questions.
Okay, so the excitement plays a very important role to keep up with the project and also to kind of deal with the throwbacks, I suppose.
Of course, yes.
I have a question here in the audience. Can you please come to the microphone and ask your question directly, so you in the audience won't see him, but you will hear him, Professor Genzel, you as well. Go ahead, please.
Yeah, hello, this is Gerd Leux. Reinhard, I have a question regarding, you mentioned this future project of 3 satellites laser equipped that can measure gravitational waves of very long wavelengths. Did I understand correctly that you think that could give you more information about the black hole in our galaxy, or was it more a general comment?
It's a more general comment, Gerd, because if you think about the sort of the crowning experiment, at least from the sort of realistically achievable side, then it's this no-hair theorem, the Schroeder no-hair theorem. And for this, you want to come as close as you can to the event horizon. So the ultimate experiment, I think most people would agree, in terms of making a super accurate measurement of the no-hair theorem, is the in-spiral of a stellar black hole into a massive black hole. And with a gravitational wave interferometer, you can do that. And you can also make this measurement of a long period of time. The current measurements from LIGO are indicative, of course, but they're not good enough because with stellar black holes merging and inspiraling, you don't have much time, only about 100 milliseconds. Whilst if you have a stellar black hole merging into a big black hole, you have a long time over which you can follow the system and build up signal-to-noise ratio. So, if we, with our techniques, are lucky, we might get a 10 sigma, 5 sigma detection of the whole no-hair theorem, with a big telescope. So my personal favorite is LISA, if it works well. And I very much hope that the German colleagues who are actively working on that in the Albert Einstein Institute will be able to do that, and then in fact get a, 100 sigma type detection of the no-hair theorem.
Yeah, thank you. And if I may, one thing I didn't understand is the spin of the black hole. How would you be able to get information about this? That seems to be difficult for me.
From finding a star which is still further in, and then we can see the lens tearing precession. The lens tearing precession is still more strongly dependent on radius than the Schwarzschild precession. And so you have to have a star which is about a factor of 2 further in. That's at least what our simulations indicate. And so, in fact, the pictures which you saw from this year are tremendously encouraging, because in a way, when the star S2 passed in 2018, we had a little bit of feeling, okay, now it will take a long time until we see more stars so close to the black hole. But no, this year it was like New York City at night. I mean, you see all these stars swirling around there. And so the chances are that with more upgrading of the sensitivity, we can look very, very close. And if you're lucky, if nature is willing to give us a star very close, we could see the spin.
Thank you very much.
Thank you for these questions. We see them popping in as well, and I'm very sorry we don't have the time to answer them all. I'd like to hand you over one last question. Could black holes eventually cause a threat to Earth someday?
Very unlikely. You see, the growth of black holes strongly coupled with the growth of galaxies. So basically, galaxies grow or form by dark matter being strongly concentrated in fluctuations in the expanding universe, and then gas falling in, forming stars, and also falling in and forming the black hole. And so the black hole and and its hosting galaxy grow together. But as the universe expands, and in fact we now think it's an accelerated expansion, the amount of gas coming in is ever less. So the black holes will not grow much anymore, at least most of the time. And so we are pretty safe out at 27,000 light years from our black hole, it won't affect us. However, if you were in a quasar and you are, say a star or a planetary system only a few thousand light years away from the center, that might be very dangerous.
Okay, so as long as we are here and we're not a star over there, we hope we are safe. Thank you very much for this amazing talk. Thanks to the audience for all your questions. We are very sorry we do not have any more time to answer all of them. Many were very scientific. Maybe there's a possibility for you, Professor Genzel, to make like an open Ask Me Everything session. This would be fun. Many people would come. We are now looking forward to the next lecture of the Nobel Talks, maybe next year, as an attendance event here in Beutenberg campus in Jena. This would be great. For now, it's my turn to say thank you to the audience who participated via the YouTube live stream. Thank you to you, Professor Genzel, for giving us all these insights. You still stay with me because we here will have another event. But for now, I say goodbye and thank you for your attention.
Thank you.